The dispersive networking solutions represent a new era of cybersecurity. Dispersive eliminates the traditional single path version of a VPN that is susceptible to increased security threats through exposed public IPs and open firewall ports, choppy performance, as well as packet loss and latency. Our radically different cloud native approach to virtual networking delivers new levels of security, reliability, and performance and provides a foundation for innovation and transformation across industry verticals. Inspired by battlefield proven wireless radio techniques, the dispersive platform dynamically splits session level IP traffic at the device, edge, or cloud into smaller, independent, and individually encrypted packet streams. The dispersive architecture is made up of multiple components that work together to form the complete solution. The solution has two planes of operation, the control plane and the data plane. Let's start with the control plane. The orchestrator, controllers, and session controllers work to convert provisioning and configuration into the actual functionality of the network. The orchestrator is the web-based UI used to do the provisioning. This sits on top of a REST API that can be used for automation and scripting. The controllers are the brains of the network. They're responsible for generating encryption keys, authenticating the various nodes within the network, and distributing in real time all the provisioning to the various components. The session controllers serve a more specific purpose. They're responsible for indicating to two nodes that want to communicate within the network which of the various data deflects they will use based on optimal current conditions. The second half of the diagram shows the data plane of the network. We have two examples of data flow in this picture. The top example is a site-to-site or gateway-to-gateway example. The bottom example is an end-user device connecting into either a cloud or a branch office, but it's the same style of transmission for data. The source device, on the left-hand side of the diagram, splits the data, sends individually encrypted streams of data to various data deflects, and the receiving end in the diagram on the right side will reach out to the same data deflects, pull that data in, decrypt, reorder, reassemble, and send the data to the final destination. It's important to note that this is a call-out architecture. The sender and receiver both call out and meet in the middle at the data deflects in the diagram. This means that the receiving end does not have to sit with open inbound firewall ports, which is another common place for malicious actors to attack. The data deflects in the middle of the diagram are a key distinguisher for the dispersive architecture compared to traditional point-to-point connectivity. Deflects serve as the waypoint nodes from sender to receiver. While the data deflects cannot decrypt the actual data payload, they can authenticate all incoming packets and ensure that only expected and permissible packets are transferred. Data deflects are constantly monitoring for things such as DOS attacks, replay attacks, or malformed packets, and they can report those issues to the control plane to roll data if needed. Data deflects also constantly look at things like RTT, latency, network congestion, dropped packets, and essentially all real-time network transmission statistics in order to allow the session controllers to select optimal deflects upon the stand-up of new sessions. All of these components work together to form the complete dispersive solution. The solution was designed to be deployment agnostic, meaning that any of the components that you see in this diagram can be deployed anywhere that you have compute, whether that's all in cloud, all on-prem, a hybrid mixture of both, and across multiple types of clouds. This allows the solution to be extremely flexible and be deployed to meet the use cases of any individual customer or partner. In today's demo, we will do a direct comparison between a traditional IPsec VPN environment and a dispersive environment. For both scenarios, we'll use an AWS-based deployment. For our IPsec VPN solution, we've deployed an OpenVPN client in the AWS US East region and an OpenVPN server in the AWS US West region. There will be a static nailed-up VPN tunnel between the two locations. On the dispersive side, we similarly have dispersive nodes deployed in AWS US East and AWS US West, with the addition of data deflects spread throughout the United States. We have a couple of deflects deployed in the AWS cloud itself, as well as bare metal-based deflects deployed in San Jose, Los Angeles, and Atlanta. Instead of a static nailed-up connection, the dispersive protocol will split the data and use multiple active-active channels to form one single session of data transport. In the case that something happens with one of these channels, for example, in the Atlanta region, We can roll that data directly to another channel without losing the overall performance of the session and continue to have the data transmit seamlessly. For the purpose of today's demo, we will demonstrate data flow in both systems using a 100 megabyte file transfer from the West Coast server to the East Coast clients. On the right-hand side, for the industry benchmark VPN, we'll use a tool called EtherApe to do packet visualization. As I start the file transfer in both systems, you can notice the EtherApe window showing all packets on the VPN side moving from the singular WAN link to the VPN server through a single tunnel. On the dispersive side, we have 6 available deflects that can be used in this system, a combination of bare metal data center deflects and AWS cloud-based deflects. I'll use the orchestrator tool to visualize exactly what's happening with the data flow in the dispersive system. As we take a look at the session graph, you can see there are 3 channels that make up the single session of data transfer. We're using a combination of these 3 deflects that have been optimally selected based on real-time current network conditions. What I'd like to do is demonstrate the self-healing capabilities of the network. We're going to manually remove one of the current in-use deflects from service. This could simulate a DOS attack, a replay attack, network congestion, a latency spike, any number of performance or security reasons that would indicate to the system that the path is no longer optimal or secure. You can see that the system immediately spins up 2 new green paths, and 2 of the previously green paths move to the orange dropping state, indicating that they're no longer in use. The system is able to autonomously detect issues and route around them in real time without stopping the file transfer that was happening, as you can see on the left-hand side of the screen. From an end-user perspective, data continues to flow and the system continues to work as intended. We'll take one final look at the side-by-side comparison between the 2 systems. You can see that the VPN system is at 2 going on 3 file transfers, and the dispersive system is at 18 going on 19 transfers. Even though we're using a highly secure protocol, we're approximately 9x faster in terms of overall throughput and data flow. In conclusion, the dispersive solution offers a handful of advantages over a traditional IPsec point-to-point tunnel solution. Active-active multipath transmissions allow for highly obfuscated transfer of data. Data deflects bring resiliency and autonomous self-healing with intelligent routing decisions. The solution architecture allows for increased throughput and bandwidth, and the final result is a high-performance, military-grade security solution from end to end.